Today we're going to talk about the second part of thermodynamics. Several months ago, actually, we talked about the first part, which primarily had to do with the conduction of heat and changes of heat being passed from one object to another through direct contact. Now we're going to talk more directly about the various aspects of heat production through chemical reactions, and particularly spend quite a bit of time talking about randomness and spontaneity. This cartoon talks about the facts of life. Now, in the second law of thermodynamics, I thought I'd put a more important fact of life below that. For when we were yet without strength, in due time Christ died for the ungodly. Geysers, as shown in this picture, are a dramatic display of a thermodynamic principle in nature. The water inside the earth heats up, and as it heats up, it builds up pressure. And it rises through to the surface through very small channels. As the pressure builds up, the water turns to steam, and then the steam is then forcefully expelled through a hole in the surface. Now, this is a dramatic example of an increase in entropy, as you'll see as we discuss the entropy. Now, spontaneity means a process that occurs naturally under certain conditions. That is, it does not require any external help. You don't have to heat it up. You don't have to add anything in particular. If you just leave it sit, then a spontaneous process will proceed without any outside influence. This graph actually shows two spontaneous processes, one of which is spontaneously quick, that is the decay of technetium, and one of which is spontaneously slow, that is the decay of uranium-238. So something being spontaneous does not take into account how long it takes for that spontaneous process to occur. Another very slow spontaneous process is the conversion of carbon from the diamond allotrope to the graphite allotrope. This occurs spontaneously at ambient pressures, but its rate is extremely slow. The process can be sped up by heating the diamond up. And this process, by the way, is called graphitization. But you can change the conditions involved by and thus change the rate at which a spontaneous process occurs. You can also, by changing the conditions, turn a non-spontaneous process into a spontaneous process, or vice versa, a spontaneous process into a non-spontaneous process. If two systems are connected by a closed valve and one system has an ideal gas and the other is a vacuum, when you open the valve, the gas will flow from one side to the other, and you'll have an equal distribution of molecules between the two vessels. This is a spontaneous process. Now, it's not spontaneous for all the molecules to decide to gather in one vessel on their own. Similarly, when you put two objects in contact with each other, the heat will flow spontaneously from the hotter object to the cooler object. So what you see here is two objects. X is hotter than Y, and then on the right they're brought into contact, and heat flows from X to Y. That is, the energy that is contained in the molecules of X is transferred to the molecules of Y, and ultimately the average energy of the two objects will become the same. Now we're going to look at three processes here, and you need to think in your mind what is happening that is spontaneous. So A is a solid, maybe carbon dioxide solid, subliming, that is converting directly from a solid to a gas into carbon dioxide gas. How is the matter being redistributed in this spontaneous process? If you think about it, what is occurring here is the solid molecules, which are fixed together in a fixed lattice, are breaking apart and distributing themselves in a much more free form known as a gas without passing through a liquid phase. The second is an example of water vapor that's in the air around this glass coming in contact with the cool glass and condensing into a liquid. It's somewhat the opposite of what is happening in A, in that the molecules go from, and they do so spontaneously in the presence of a lower temperature, they go from a gaseous state to a liquid state, or a more ordered state, and this is because the temperature is lower. The last is when you drop food coloring into a clear glass of water, spontaneously the color molecules will distribute themselves equally throughout the entire liquid. And again, this occurs without any external input. Now, these two handsome gentlemen are two guys that looked at the idea of entropy and heat exchange. The first is Carnot, and the second is Clausius, and they both looked at something called a reversible process. A reversible process is a process that progresses in one direction at a slow rate, is in equilibrium, and can be reversed if the conditions are changed modestly. And if you want to read more about what Carnot did, you can look up what's called a Carnot cycle or Carnot engine, and it will explain how he used small changes in the conditions to cause reversing of a process that's generally spontaneous. Entropy is the degree of randomness in any system, and the change in entropy, represented as delta S here, is equal to the amount of heat required to reverse a reversible process divided by the temperature at which this condition is undertaken. And so this is an important concept to remember about entropy. That is, the change in entropy in any system is how much energy in the form of heat you'd have to put into that system in order to reverse the change, and that amount of energy divided by the temperature at which it occurs. So as I said, the first fellow on the left here is Nicolas Carnot, and he did research in steam-powered engines, and he, along with Rudolf Clausius, who later studied the same thing, looked at spontaneous heat flow processes, and you'll find something called isothermic expansion, which is expansion at a constant temperature, and adiabatic expansion, which is expansion at a constant heat. And you see that heat and temperature are the two things that take into account the randomness of the system. And so he was able to show that the most efficient way to do that is to do intermittent expansions and contractions with intermittent changes of conditions. Now we're going to look at something that some students have difficulty understanding, but just take your time and think about this, and I think you might be able to understand what the book is trying to explain. It's trying to explain to you in picture form how systems tend to want to achieve a site of greatest randomness or greatest entropy. So at any particular configuration and location of molecules and energies that a system would find its atoms and molecules in is called a microstate. So the microstate is defined as the arrangement of molecules and atoms and the amount of energy that each of these molecules and atoms has. And that's called a microstate. And so if you define a microstate that way, then the entropy of any microstate the entropy of any system is equal to a constant times the natural log of that particular microstate. And so if you think about it for a second, the amount of random motion or amount of randomness that a system would have to be dependent on the configuration and location of molecules in the system, as well as the amount of energy that each of those molecules has. And so this mathematically basically sets up the idea that the entropy of any particular system is equal to a constant times the natural log of that microstate. And so the change in entropy is going to be the final entropy minus the initial entropy, which is going to, because we're talking about natural logs, when you subtract natural logs, it's the same as dividing the two numbers. And so if you subtract the initial natural entropy from the final entropy, it's equal to the natural log of the final microstate divided by the initial microstate. And if you have any system that has n number of particles in a little n number of boxes, then the total number of options that you can have is little n to the big nth power. And the most probable distribution of molecules will be, or particles, will be the one that has the greatest final entropy. And that's what this is supposed to show. You start out with four particles, so big N is 4, and you have two boxes, which looks like dominoes. A single domino is the two boxes attached to each other. And so the total number of possibilities is 2 to the 4th power, and 2 to the 4th power is 16. So there's a total of 16 possible arrangements of particles between two boxes that have 4 particles. And so the microstates can be collected based on how the molecules are distributed. And what you can see is that A and E are the least likely because they have all 4 particles in one box or the other. B and D show the next less likely because they show all the particles distributed unevenly. And then C shows the various distributions that are most likely and have the greatest randomness. Now, any particular one is more likely or less likely in the C row. Any particular one would depend on other factors other than just the number of particles. Factors such as attractions or repulsions between the molecules or energy levels in the molecules and so forth. Another way to think about this is, imagine you saw the previous slide where I showed you the gas molecules in the two. Imagine this is gas molecules between two vessels, and you open the stopcock between the two. What are the most likely distributions to see? And C would be the most likely distribution. Now this model shows the same idea, except it's visualizing heat or energy from a hot object to a cold object. The heat is represented by stars, and the molecules that contain the heat are in the top A and B, and in the bottom C and D. And what you can see again is the middle row is the most likely, where you have a single heat value distributed between the two boxes. And then you can have various possibilities as to which of those two molecules in each box has the additional heat energy. So before the heat flow occurs, the objects that comprise particles A and B contain both units of heat, and are represented by the three possibilities. However, when they come in contact with each other, then there's an even distribution between the two boxes, and the heat is dispersed in the various microstates that are shown. And C cannot occur or does not occur in nature spontaneously, because it would represent a less random situation and something that doesn't happen in real life. Now take a look at this. It says, consider the system shown above. What is the change in entropy for the process that converts the system from initial to final? So here's initial, is the four globes together, and then you have all these various possibilities that can occur after that. The change in entropy here would be from one microstate to 6 different microstates. Now, if we were going to show this mathematically, it would be as follows. The log, or the constant for this calculation, and it's just something that is given to you, is 1.38 times 10 to the minus 23. You have 6 microstates in the final and 1 microstate in the initial, and so it's 6 over 1. So it's 1.38 times 10 to the minus 23rd times the natural log of 6, which is 2.47 times 10 to the minus 23rd.